Physics Made Easy channel. And now the 15th question which I have left last time. The basic statement of this question is for sound waves, Doppler formula for frequency shift differs slightly between two situations. We have got two situations. One is this. So this is Doppler formula for sound. Note it down very clearly that this is Doppler's formula for sound. And let me make it focused. This is Doppler's formula for sound. This is for sound waves. Note it down. This formula is for sound waves. This case is when source is at rest. Source is at rest and observer is moving. This is source and this is observer, and it is moving with velocity VO. The formula is this. It may move towards it or move away from it. If moves away, then it's positive, otherwise it is taken as negative. And in second case, this is the formula when this is source and this is observer. This is source and this is observer. Source is moving towards it or moving away from it. The plus sign for moving towards it and moving away from it, we take negative sign. So this is observer. Now these two formulas, they are different. So that's why we say that in case of sound, Doppler effect is asymmetric. And also notice that there is only longitudinal Doppler effect in case of sound. And now let us shift directly to the case of light. Now the two formulas are different. Important point is these two formulas are different. The two formulas are different because motion of observer relative to medium is different in the two situations. Now, for light wave in vacuum, no such relative motion between observer and medium. So this is due to the special theory of relativity by Albert Einstein, which says that velocity of light remains constant in all inertial frames. So that's why the situation is same in case of light waves. Hence we only observe the relative motion between the source and observer. That is only counted in this case because the velocity of light remains constant in all inertial frames. Inertial frame is, we say that one frame of reference. Let me draw a diagram here. Suppose theory of relativity says one is this and other is this. I am taking the simplest case. What theory of relativity says? Let this be a frame of reference. Here, their x-axis coincide. One is, this is O dash and this is O. I am taking two frame of reference. Frame of reference is coordinate system plus timer placed at origin. And here the timer placed is T dash. This is moving with constant velocity V. Then the velocity of light is same in both these frames of reference. Now, that's why we haven't taken relative motion between the medium and source or observer into consideration, and we have got symmetric formulas for the motion, and we only take relative motion between source and observer. We don't consider relative motion between or the relative motion of the medium or the relative velocity of light with respect to medium. Why? Because of the special theory of relativity, which says that the velocity of light remains constant in all inertial frames of reference. Now let us have a look on this next problem. It's a very easy problem. We have already done it in a double slit experiment using light of wavelength 600 nanometer, angular width of the fringe formed on a distant screen is 0.1 angstrom. What is the spacing between the two slits? This is the formula that we shall be using. Theta is equal to lambda by d. We have already done questions of similar nature. And now, the very next question. Answer the following questions. In single slit diffraction experiment, the width of the slit is made double the original width. How does this affect the size and intensity of the central diffraction band? So we have got a formula for central diffraction band. I will show you the formula from this diagram. And I will also show you the diffraction pattern. So this is the central maxima. Yes, we will have to wait for a minute. A is the width of the slit. And now this is the formula for width of central maxima. So first of all, this is the diffraction pattern. This is the diffraction pattern, width of central maxima. This is the width of central maxima. On diagram, this is the width of central maxima. And this width is equal to one theta angle in the upper portion, another theta angle in the lower portion. So width of central maxima is 2 theta. And theta is by one formula lambda by a, by other formula x by d. This is x by d, we calculate the tangent theta. So we have got two formulas for width. And these are these two formulas. One is 2 lambda by a. Now this is the formula which I shall be making use of here. So in this case, the width, how does this affect the size and intensity? Now the size, width of central maxima, I have already said this is 2 lambda by a. Larger the width of the slit, sharper will be the central maxima. And the second part is intensity. As you will increase the width, more and more light will fall, and intensity of the linear width is given by this. He has given us the formula. D is the slit width. I have already told you, if we make it double, then the width of the central maxima will be halved. Now because the width of the central maxima is halved, it means area will become 1/4 and the intensity will become 4 times. Same light will now focus on lesser area, an area which is 1/4 of the original area. It means the intensity will increase 4 times. By other logic, as we are increasing the slit 2 times, that will increase the amplitude of light reaching there by 2 times, and thereby intensity 2 square means 4 times. So one logic is quite from one logic. So let me make this logic once more clear. We are saying that if we increase the width of the aperture, this is the width of the aperture in this diagram. If we increase this width, then the width of central maxima decreases. Now as we increase this width, it means more and more light will fall on lesser and lesser area. And intensity is energy per unit area per unit time. As the area is decreasing and energy falling is increasing, so this directly means that it will increase the intensity of the central maxima. So this is quite clear. This width will decrease. Decreasing width means its height will remain constant. If I draw a diagram, let me now draw a diagram here. Let this be the straight line. This is the straight line. Now let us say this was the original width of central maximum. This was the original width. Now it is becoming sharper and the width will remain to be this. This is the final width. Now the whole of the light that was falling in this area is now falling only in shaded area. And also because of increase of width, more and more light will focus here. Now what is important, energy falling has also gone up and area has gone down. And intensity I is energy falling, energy represented by E per unit area per unit time. Now this has increased and A has decreased. Combined effect is intensity will increase, and it will increase approximately by 4 times the initial value. Now let us take the second problem into consideration. Second part, in what ways diffraction from each slit related to interference pattern in double slit experiment. So this is an important part again. In double slit experiment, interference pattern is observed by waves from two slits. In diffraction, they are secondary wavelets from same slit. Now in this case, but as each slit provides diffraction pattern of its own, thus the intensity of interference pattern of Young's double slit experiment is modified by diffraction pattern of each slit. Now, again question, in what way diffraction from each slit related to interference pattern in double slit? So I will just now if diffraction takes place, I will draw the pattern. In double slit experiment, an interference pattern is observed by the waves of the two slits, but each slit provides diffraction pattern. So I will draw the diagram, all the three diagrams here. First diagram for the diffraction pattern he has asked. Now the diffraction pattern in double slit experiment, this is the diffraction pattern. I am making the height of the central maxima slightly lesser because of space. Now inside this diffraction pattern, there is interference pattern like this. This is interference pattern. This is interference pattern in case of double slit diffraction. So interference pattern has been modified by diffraction pattern. So this pattern has been modified by diffraction pattern. Now single slit, this is the diagram for only interference. In case of interference, the height of fringes or the brightness of fringes is same. And in case of diffraction pattern, it goes on increasing. And this interference pattern has been overlaid by the diffraction pattern. So their height should be same. There is a bit of error here. So all this is interference pattern. I am representing it by I. And this is combined interference and diffraction pattern that usually take place. And we are familiar. This combines with the pattern that I am going to draw here. This pattern combines with another pattern which is diffraction pattern. And diffraction pattern Now we were just talking about the two patterns. One pattern was this is only diffraction pattern. I will just represent it by D. So this diffraction pattern of each slit combines with the interference pattern due to the two slits. Now this is the diffraction pattern due to single slit. This is single slit. We have got diffraction patterns like this. And now due to double slit, we have got interference patterns as I have just indicated in the diagram, and I want to show you the exact diagram. This is the exact diagram. So we have got interference pattern due to this. Now these two slits, this slit will produce its own diffraction pattern, this slit will produce its own diffraction pattern provided the width is comparable to the incident wavelength. So two diffraction pattern one due to slit A and other due to slit B, that will combine due to the interference pattern due to both the slits. Now again coming to the problem, this is the diffraction pattern of one slit, similar diffraction pattern of the second slit, that will combine to the interference pattern of the two slits, and the final pattern will be this. The outer profile, yes, in this diagram, these two diagrams are the same. This outer profile is due to diffraction, and this inner profile, which is red in color, is due to interference. So with these words, I finished today's lecture, and next we will cover in my next lecture. Thank you very much for being with me for such a long time, and kindly comment on it if you find this lecture to be wanting in something, or you can also share it if you like it. Thank you very much for being with me.